Redox processes HL2, electrochemical cells. Essential ideas. Energy conversions between electrical and chemical energy lie at the core of electrochemical cells. Nature of science, employing quantitative reasoning. We use electropotentials and the standard hydrogen electrode in calculations. Collaboration and ethical implications. Scientists have collaborated to work on electrochemical cell technologies and have to consider the environmental and ethical implications of using fuel cells and microbial fuel cells. The three applications of electrolytic cells, as seen previously in a previous presentation, we have electrolysis of molten salts, electroplating, and electrolysis of aqueous salts. For electrolysis of molten salts, the extraction of metals, non-metals from compounds in liquid form. For electroplating, and the application, it is the application of a thin layer of a more expensive metal onto another normally less expensive metal. And finally, the electrolysis of aqueous salts, the purification of elements and other substances from water or compounds dissolved in water. Okay, let's look at electrolysis of molten salts. We do calculations here. The minimum voltage for electrolytic cells. What is the minimum voltage required for the electrolysis of sodium chloride? First, we'd write out what the anode reaction is, and then the cathode reaction. We look at our table, and we'll do the overall reaction first. Then we look at our table for cell potentials, write them down, and you can add them up as we've done in the previous presentation. And we have this cell potential. We can see it's negative, we know it's non-spontaneous. And the voltage required for it to occur would be 4.07 volts. So if we had a battery in there, we would need to have a potential difference of 4.07 for this reaction to occur. Electroplating calculations. We use these two formulas and we can calculate the mass of metal plated. Q stands for charge in coulombs. L, or capital R should I say, is the current in amperes or amps. T is the time in seconds. Ne is moles of electrons transferred. And F is Faraday's constant. Let's do an example. Calculate the mass of copper plated on a key if a current of 0.50 amps runs through the cell for 1.0 minutes. So what would you do first? First of all, we'd calculate the amount of charge transferred during the running of the cell. So we'd use Q equals I times T. We can put the current in, as in the question, convert minutes to seconds to get the charge in coulombs. Next, we calculate the amount of electrons transferred in moles. We just calculate the charge and we know Faraday's constant, so it's a simple case of plugging into the formula to find the number of electrons in moles. Next, calculate the amount of copper formed in moles. Well, we know to fully discharge copper, we need 2 electrons for every 1 ion. And so we've got 3.11 times 10 to the minus 4 moles, but we need 2 moles of electrons for every 1 mole of copper. So we'll use this conversion factor to calculate the number of moles of copper that we have. And finally, we can use the molar mass as a conversion factor to convert the moles of copper into the mass we have. You can see there's a bit of a mistake going on there. That should say moles of copper. Here's another example. What length of time would be needed to plate 8.88 times 10 to the minus 3 grams of gold from a solution of a gold chloride given a constant current of 25 milliamps? First step, we can calculate the moles of gold plated because we have the mass given here. We'd use molar mass as a conversion factor to convert grams into moles. Next, we need to look at how many electrons are required to totally discharge the gold, and you can see for every 1 gold ion you need 3 electrons. So our conversion factor to go from moles of gold to moles of electrons would be a 3-to-1 ratio conversion factor. Next, we can calculate the charge because we have our formula here. Plug in number of moles of electrons which we have, plug in Faraday's constant, rearrange it and calculate charge. And next, to calculate the time required, we can use the other formula, plug in the charge which is calculated. We have 25 milliamps up here, which we convert to amps, rearrange the formula to calculate time in seconds. Okay, factors affecting the amount of product formed. First of all, the charge transferred. The greater the charge or number of electrons transferred, the greater the amount in moles of product formed, which is kind of straightforward, sensible. And you can see it by looking at the formula. Obviously, if you increase the current, you increase the product. And if you increase the time, you increase the product. Because you're increasing the charge. If current is increased, the charge is increased. If time is increased, the charge is increased. And the greater the charge transferred, the greater the amount of product can be formed. The charge on the ion also affects the amount of product formed. The greater the charge on the ion, the lower the amount in moles of product formed for any given value of Q. And you kind of just saw that in previous examples. We've got moles of, if we're calculating moles of silver here, it's a 1-to-1 ratio when converting moles of electrons to moles of silver. We use conversion factor of 1-to-1. However, if you require 2 electrons to totally discharge a metal ion, such as copper, well then when you're converting the moles of electrons to moles of copper, your conversion factor is a 1-to-2 ratio. And so you're going to only create half the number of moles in this scenario. Just notice this little starred section here. If the charge Q transferred is the same, the total number of moles of electrons gained is the same. But the moles of product depend on the moles of electrons in the equation. Electrolysis of aqueous salts. What are the reactants in an electrolytic cell with inert electrodes? Well, the anions, we have the cations, the negative anions, the positive cations in the electrolyte. The anions move to the anode, the positive anode, and cations move to the negative cathode. The anions are then oxidized. Remember anox, red cat standing next to an ox. And the cations are reduced. And ions are usually discharged to form an element, which we've seen many a time. 4. Electrolysis of aqueous salts. How are the reactants different in the electrolysis of a molten salt versus an aqueous solution of the same salt? So what's the difference between having a liquid salt as opposed to a salt dissolved in water? In addition to metal and non-metal ions reacting at the electrodes, water can also be oxidized or reduced at one or both or neither of the electrodes. So with molten salts, only the metal cations are reduced at the cathode, and only the non-metal anions are oxidized at the anode. But if you have that salt dissolved in water, then both the metal cations or the water can be reduced. With the non-metal anions or water being oxidized at the anode, which kind of makes sense if water is present. What happens if water is reduced or oxidized during electrolysis? Well, it's obviously going to be reduced to the cathode. The water reacts with the electron to give hydrogen gas and an hydroxide ion, and it's oxidized at the anode, where we get oxygen gas and we get H plus, so it's becoming more acidic. The evidence for reduction at the cathode of water is bubbles of gas form, and you can use litmus paper, which would turn blue, showing that OH minus, because we are forming a base. At the anode, we know it's being oxidized if there's bubbles of gas, and if litmus paper turns red, because you're forming an acid. What happens if water is reduced or oxidized during electrolysis? You can do this demo next time you're in the lab, unless of course you're in the lab right now, whereupon you could do it right now. Electrolysis of aqueous salts. Selective discharge of ions in the electrolysis of aqueous solutions. Metal cations that are stronger oxidizing agents than water are selectively discharged by reduction to form the metal. But if the metal ion is a weaker oxidizing agent than water, then water is reduced to form hydrogen gas and OH minus ions. So if you have a look at the reactivity series here on our table, we know that the weaker oxidizing agents are at the top and the stronger oxidizing agents are further down. You can see where water is, and so you just need to look at whether the metal ions are above or below water to see what will be oxidized. Things that are above, all of these ones here, will not be reduced. But these ones here will be. Okay, let's have a look at the anode. Question A. You've got iodine or water. Have a look at your table. Which substance is selectively discharged at the anode? That's right, it is iodine. Write down the half equation from the table, and what would you see? Well, we're getting iodine formed, so we're going to see the formation of a brownish solution. Next, dilute chlorine or H2O. Have a look at your table. What do you think? Yep, this time it will be the water. So we're going to get oxygen gas formed, and you can see we're getting an acidic solution. So we're going to see some bubbles of gas because of the oxygen, and a universal indicator will turn red. The last one, have a think about it. Be the water. And why would it be the water? Well, it's going to be the water because the sulfate ions can't be oxidized, they can only be reduced. So there is the equation again, and we're going to get bubbles of gas, and universal indicator would turn red. Okay, electrolysis of aqueous salts. Let's have a look at some examples of electrolysis of aqueous salts. What about if we just have distilled water with inert electrodes? So just pure distilled water. The only substance present is water, H2O. So the substance that may react at the cathode would be obviously water. Half reaction, we've got water forming hydrogen gas and hydroxide ions. And we know the bubbles of gas form because of hydrogen, and the solution becomes basic, an indicator will turn blue. And what about substances that react at the anode? Again, obviously just water. Half reaction, we're getting oxygen gas formed and the hydrogen ions, so becoming acidic. We see bubbles of gas from the oxygen, and a universal indicator would turn red. What about if we have dilute aqueous sodium chloride with inert electrodes? Substance present, we've got sodium ions, chlorine ions, and water. Keep that table handy. We can think which substance may react at the cathode. Well, it's going to be sodium or water. Okay, well, which one will it be? Well, it's going to be the water, isn't it? And so water reacts to give hydrogen gas and the hydroxide ion, and obviously bubbles of gas, and indicator will turn blue. What about what may react at the anode? Well, it's going to be chlorine or water. Quick check of the table. We see again it's going to be water. So with dilute aqueous sodium chloride, only the water is discharging at the electrodes. Supporting evidence is the same. We've got gas forming because of the oxygen and it's becoming acidic. So let's try a different salt. What about potassium bromide? So we've got potassium ions, bromine ions and water. The substances that may react at the cathode are going to be the potassium ion or the water. Quick check of the table to see which one will. It's going to be the water. So we're going to get bubbles of gas and it's going to become basic. And this time, the substances that may react at the anode, well, we've got bromine ions or water. Which one will it be? This time it's going to be the bromine. And so bromine ions are going to form bromine, a diatomic molecule. And supporting evidence, well, we're going to get a yellowish brown liquid forming because of that bromine. What about dilute aqueous copper 2 sulfate? So we've got copper ions, sulfate ions and water. Substances that may react at the cathode are going to be the copper and the water. Quick check to see which one is more likely. And you'll see it's going to be the copper. So we're getting copper formed, copper metal forming. You get a reddish brown metal which plates the cathode. And will it be the sulfate or will it be the water discharging at the anode? It's going to be the water. And so we're going to get the oxygen formed and an acidic solution. The factors that affect the products formed, it's not as straightforward as we've just seen. And you might have noticed I mentioned dilute chloride ions previously. So let's have a look at this. Well, first of all, the position of the substances in the reactivity series matters. And we've been using that table throughout. So that's kind of straightforward. You've seen many examples now. And the position in the reactivity series determines whether an ion or water is selectively discharged. During the electrolysis of an aqueous solution, you just look it straight up. If you had it in a test, you could even highlight water and then just like look above or look below. But the concentration of the anion in the electrolyte always also affects products formed. This applies mainly to the chloride ion, and we're going to look at a later slide there. And the type of electrode also matters. Inert electrodes versus metal electrodes. And again, we'll have a look at the later slide. So, the effective ion concentration. The electrolysis of aqueous sodium chloride. So mainly just looking at the chloride ion here. At the cathode, with dilute sodium chloride, is it sodium or water? Well, we know already that it's water because we looked at that in the previous slide. And so we're going to get hydrogen gas and the hydroxide ions forming. What about the anode? We know in dilute sodium chloride that it's the water again. But what about when it's concentrated? Is it going to be the Cl- or is it going to be water? It's actually the Cl- at concentrated, which you could probably guess because the slide wouldn't exist if it was just the same. And the chlorine is going to form chlorine gas. Okay, electrode type. And this time we're going to look at copper. So at the cathode, if we're using inert electrodes, such as graphite or platinum, we know that the copper discharges to form copper solid, copper ions. And what if we've got copper metal electrodes? Well, again, it's the copper, so no change there at the cathode. So you can probably guess what's going to happen, right? At the anode, when we use inert electrodes, it's the water that is reacting at the anode. So is it going to be the sulfate, the water, or the copper? Well, it's going to be the copper. And we're going to get copper ions forming at the copper metal electrode. So there's a difference there too. Okay, we're going to summarise the electrolysis of aqueous salts here. At the cathode, which has a negative charge, we have a reduction reactions, and we know that the metal cation or water can be reduced, and whichever is a stronger oxidizing agent will be discharged. Dilute versus concentrated chloride makes no difference, it's the same at the cathode. And copper electrodes, it would make no difference if you use a copper electrode instead of an inert electrode, it's still the same as above. So things change in the anode, don't they? The anode's positive, things so where oxidation takes place. The non-metal anion or water can be oxidized. And the preference would be that the stronger reducing agent undergoes oxidation. The difference between dilute versus concentrated chloride ions is that with dilute chloride ions, the water is oxidized, but with concentrated chloride ions, the chlorine ion is oxidized to chlorine. And if we use copper electrodes instead of inert electrodes, then copper solid is oxidized in preference instead of the ion or the water to form copper ions. And that is the final slide. Splendid.